Okay, let's get started. So you might notice that I'm not Professor Mike DeWeese. My name is Tristan Smith. I'm actually lecturing for the other lecture section, which meets Monday, Wednesday, and Friday for 8A. So both Mike and I are following pretty much the same syllabus, and he couldn't be here today, so he asked me to cover for him. And so first of all, here's information. Master your physics 8A. Good information. I'm going to take this down now because we're going to use this in a second. The reading, this is the same reading that should have been up here as well for this week. Chapter 4, which is talking about Newton's laws of motion. Chapter 5 for next week, which is the application of Newton's laws, but you guys have actually already covered some parts of that. Actually, this inclined plane here is a good example. And then 3.6, because circular motion is also going to be next week. So just to give you a quick introduction to who I am besides the other instructor for 8A, I'm a postdoc here at Berkeley. I work in theoretical astrophysics. So you're going to get a little bit of astronomy today from me, and then you're also going to get a little bit of physiology from me. So once we get a little bit into Newton's laws, we'll start to look at some forces on the body, which are pretty interesting, simple calculations you can do that show you how physics and understanding friction and normal forces have an application to things like physiology. We know that as a general statement, but I'm going to go through a specific example. If we have time, by the end of the lecture, we're going to see why I have 2 pieces of toilet paper taped to the table here. I don't have a cold or anything. This is not, I don't need that. This is for us to see physics in action. Okay? So let's start by just writing down, since we're actually going to use Newton's laws today, let's write down what his laws are. So the first law just talks about, in general, what it's like for an object to move without a force. So if there's no force, you have a constant velocity. That means that your speed remains the same and your velocity is not changing direction. The second law, it gives you a mathematical statement that says if there is a force, if there is a force, the net force acting on an object will result in an acceleration. And that acceleration, if you apply the same net force to 2 objects which have different masses, that acceleration is going to be different, and it's going to be proportional to the inverse of the mass. Okay, sorry about that. So that's a real simple statement, right? And I don't know, when I was learning this stuff, and I saw this equation, and I thought about the fact that it took 2,000 years of deep critical thought in the Western world to come up with this simple equation. It made me initially think, wow, humans are not that bright. It takes 2,000 years of thought to write down this equation. But you know what? This equation is extremely deceptive. From the work in kinematics that you've done, you understand what the right-hand side of this equation is. This left-hand side of the equation is a force. No one said what force it is. No one said why the force is occurring. No one told you how to compute this force. This equation is deceptive because inside the left-hand side here, the symbol F net, is everything that we see around us. Electromagnetic forces, gravitational forces, strong nuclear forces, weak nuclear forces, viscosity, the forces acting on a fly's wing. Everything is contained in this left-hand side. It's probably the most impressive generalization that the human mind has ever achieved because everything is in here. So the difficulty with dynamics, which is what we're going to work on today, is specifying what the left-hand side is doing. The third law, action is equal to minus reaction. So I put that minus sign there to remind us that the third law is saying, oh, I'm thinking I'm knocking something over. The third law is saying that the action of one force on one body is equal and opposite to the reaction of the other force on the one. So you guys are experiencing that right now, sitting in your chairs. The gravitational force on you is causing you to try and move downwards. So there's a force from you on the chair, but then the chair is applying an equal and opposite force upwards, leaving you not moving, which is good. The same thing happens when I push against this wall, right? I want to point one thing out about something like that. I push against this wall, my hand doesn't move through the wall. I say there's a force. You know what's amazing? I don't have to specify the detailed physics of why that force exists. I can just say it's there. I don't have to worry about why it is. It turns out that when you get into the details, you start to realize that this force preventing my hand from pushing through the wall is electromagnetic in nature. It's the electrons in all of the atoms and molecules in my hand repelling the electrons in the atoms and molecules in this wall or in anything else that we can't move through. But it's amazing. We don't need to know that in order to use Newton's second law. Okay. So I want to put something up on the screen, and I want you to think, if I can actually find it. Had it here. Oh, here it is. I want you to think, and this is something you're just going to take a minute to look at. I'll zoom out. So what I'm showing you here is the aerial view of some ball, let's say, that's moving around a curved surface. So there's some curved surface here. The ball is moving around, and then the curved surface ends, and you're looking down on it. It's on a table. And the question is, what direction does this ball move in? A, B, or C? Okay, I'm going to ask for hands. Who thinks A? C? B? Cool. Perfect. So it's moving in a straight line because once it exits that track, there's no force acting on it, and so it's going to just continue to move with a constant velocity. The first of Newton's laws tells us that. Okay, I have one more simple question for you, and then we're going to get into some strange consequences of the third law. Okay, so this is my way of drawing me on a bicycle riding up a hill. This is something I do almost every day, riding up on Durant up to college, and I hate it. So I'm riding up this hill, I'm going straight, and my velocity is constant. Is there a net force acting on me? Raise your hand if you think there is a net force acting on me. Raise your hand if you don't think there's a net force acting on me. Raise your hand if you didn't vote. There were only 2 options there. Should see more hands for that one. So the reason I bring this up, first of all, we see there's no change in my velocity. Without any other thought, you can say, Newton's first law tells me no force, none. So the net force acting on me is 0. But if you actually look at the forces that are acting on me, there are multiple forces. I'm only going to draw 2. So there's a force acting on me due to my pedaling. We'll call this F bike. And then there's a force of gravity pulling me back down the hill. The statement that the total force, the net force acting on me, is 0 is just the statement that if we sum these 2 forces up, if these are the only 2 forces acting on me, so we have F grav plus F bike and that equals 0. So these forces are equal and pointing in opposite directions. I'm pointing this out because you know from experience, and I know from experience, that when I get to the top of that hill, I'm going to be exhausted. I hate it. I can't do it. I've been biking, trying to do that hill, thinking it'll get easier for a year, and it isn't. I still have to get off my bike at the top. This is to say that we have this concept. It seems like the most important thing in working out the dynamics of an object is the net force, because that's what appears in Newton's law here. But when we want to calculate something like energy or work, the net force is not what we're going to worry about. So it's an interesting thing to think about it. Well, then, if we don't worry about the net force, because when we talk about energy and work, it's going to be related to forces. Everything in dynamics goes back to forces. But we're not going to worry about the net force. That has no bearing on the amount of energy you expend in doing something. Okay, you know what? So let's start talking about, are there any questions, concerns? So let's start, interesting. Let's start talking about Newton's third law and some really strange consequences of the third law. So the third law makes a seemingly simple statement. For every action, and this is the typical way it's stated, there is an equal and opposite reaction. So I am going to do something very disruptive to you right now, and I'm sorry to have to do this. I have a softball here. You guys ready? Did you all feel that? Okay. So what's happening when the softball goes up? So let's look at the motion of the softball when it's at the top of its one-dimensional motion. It's going up and it's sitting there at the top. What's happening? What is the Earth doing to the softball? I heard it's slowing down the velocity, and when velocity changes, it means that we have a force, a net force. So there's a net force acting on the softball when it's at the top of its trajectory. Let me draw the situation. Not for this softball. I'm going to pick. Here we go. This room is not made for short people. Okay. I usually have a little step stool back here. So we've got the Earth. Got a circular Earth there, spherical. And for future reference, and this is my astronomy/cosmology side coming out, this circle with a plus inside is the symbol for Earth. So the Earth has a particular mass, and that mass is 6 times 10 to the 24 kilograms. So now let's look at my softball. Let's say that my softball, at the top of its motion, is 100 meters from the surface of the Earth. So the height is 100 meters, and what we know is the softball has a mass of 0.5 kilograms, half of a kilogram. So what is the force of the Earth on this ball? So we know that the ball, when it's just gravity acting, the ball has a constant acceleration. And since we know that the net force is equal to the mass times the acceleration, we know that the force of the Earth acting on the ball, so that's how I'll represent that, a little subscript. So this is Earth acting on the ball. And one other bit of notation. For this discussion, we're going to define the motion, the direction that the ball's going to move in will be our positive increasing direction. So the force of the Earth on the ball is going to be plus the mass of the ball times the gravitational acceleration. So we know what that is. The mass of the ball, we were told, is half of a kilogram, and I know I've been to a few of Mike's lectures. Gravitational acceleration is 10 meters per second squared. We're not going to worry about this 9.8. So we have 1/2 times kilograms times 10 meters per second squared. Kilograms meter per second squared is the unit of 1 Newton, and 10 divided by 2 is 5. So the force of the Earth on the ball is 5 newtons. And the last thing I want to calculate is how long does it take for this ball to come down from a height of 100 meters, given this force. So we know from our equations of motion, when an object has a constant acceleration, its height as a function of time will be its initial height plus its initial velocity times time plus 1/2 the constant acceleration in that direction times time squared. So the initial height of this ball is h. We'll put in the 100 meters in just a moment. So the initial height of the ball is h. We're going to, since it's at the top of its trajectory, what is its velocity? 0. That's my favorite number because it makes everything simple. So we've got 0. And then, since we've defined this direction, we know that the acceleration is pulling, the force is in the direction from the mass to the Earth. This is our positive direction. So we get a positive 1/2 gt squared. You know what? I want to do one more thing. Just for simplicity, I'm actually going to define this. The surface of the Earth is y equals 0. So when I do that, the initial position of this ball is actually going to be minus h. And you can see in a second, if you don't see it already, why I did that. Because if we want to know how long it takes for this ball to get from this point to the surface of the Earth, we have to set this equation equal to 0. So 0 is equal to minus h plus 1/2 gt squared. And that automatically tells us we can solve for the time it takes for the ball to go from its original height to the surface of the Earth. We can put the h on the other side of the equation, and we get 2h over g. That's our time. So let me box that. I'll put it up there. So that's the amount of time it took. And if you put in the numbers that we have here, 100 meters, that's the height, g is 10 meters per second squared, what you'll find is it takes, t squared is 20 seconds. So if we take the square root of that, t is about 4.5 seconds. So it takes 4.5 seconds for this ball to come back to the Earth. So at the same time, let's go back to this third equation here. Action is equal to minus reaction. If Newton is right, and for this, we have to believe him at the moment, because we're not talking about contact forces. So I'm pushing against this wall, and the wall is pushing back against me. That's a contact force. That's a very particular type of force. Gravity is a long-range force. There's nothing necessarily connecting this ball to the Earth. But it turns out that Newton's third law is still true. It's true in all circumstances that we've explored so far. It's in agreement with all of our experiments to within their error. So what that means is if the Earth exerts a force on the ball exerts a force on the Earth, and it's going to be equal and opposite to the force that the Earth exerts on the ball. So if the Earth exerted a force of 5 newtons, the ball is actually going to be pulling the Earth towards it with an equal and opposite force. So knowing the force that the ball is exerting on the Earth, we can now calculate the acceleration of the Earth due to that force by using Newton's second law. So we have F net on the Earth is minus 5 newtons, and this is going to be equal to the mass of the Earth times the Earth's acceleration. So we have a value for the mass of the Earth. It's 6 times 10 to the 24 kilograms. So now it's straightforward to solve for the acceleration of the Earth. And when you do that, you find the following value: 8 times 10 to the minus 25 meters per second squared. It is an understatement to say that that is a lot smaller than the acceleration due to gravity acting on the ball. But that's because the mass of the Earth is so much larger than the mass of the ball. So we can calculate how far does the Earth fall before this mass, the ball, hits the Earth's surface. So to do that, we can use the exact same equation that we had up there, except now we want to know the height, the distance that the Earth fell, is going to be equal to 1/2 the acceleration of the Earth multiplied by the amount of time it was falling for squared. So we have all these numbers. We know that this t squared is 20 seconds squared. The acceleration of the Earth is 8 times 10 to the minus 25 meters per second squared. We can put all of these numbers in. And what we find is the Earth, in the time that the ball took to come back to the Earth has come up towards the ball a distance of 8 times 10 to the minus 24 meters. Does anyone have any idea how small 8 times 10 to the minus 24 meters is? Let me give you some sense. Let me just tell you a few other objects and how small they are. An atom. An atom has a radius of 10 to the minus 10 meters. This is 14 orders of magnitude smaller than the radius of an atom. And then we can get to something even smaller. The nucleus of an atom, or a proton, 10 to the minus 15 meters. So the Earth is moving. That we can be fairly sure of. We have a lot of experimental evidence that says action is equal to minus reaction. Now, of course, I'm not even getting this up to 100 meters, so it's moving even less than our estimate here. But even if I were able to throw this up 100 meters, the Earth would be moving a very small amount. On the other hand, so I've only talked about what the Earth is doing when the ball is at the top of its trajectory. My initial act of throwing it up, well, what I need to do is I'm pushing against the Earth when I do that, and the Earth is going to feel an equal and opposite force downwards. So while you're throwing a ball up and down like this, what you're actually doing is the Earth is slightly moving up and down along with the ball, coming back towards the ball as the ball comes down, moving away from the ball when the ball is going up. To me, this example gives a visceral sense of what this type of relationship can do and the implications that it can have. This is a very strange implication. There's also implications for what the Earth does when you jump like that. The entire Earth has to move because of action equals minus reaction. So it's something to keep in mind as you're working out these problems with action equals minus reaction, that there are a lot of interesting results and strange phenomena that occur because of that relationship. And again, that relationship holds true in every case that we've looked at. Are there any questions? Okay. Does anyone have any idea what that top word is saying right there? I think I have some idea, but it's not related to our class. I did not put that there. Okay. So now, with some experience with the odd results of the third law of motion that Newton proposed, what I want to do is I want to move to a situation which is related to the third law. And that is, I want to discuss in some detail the difference. So at this point, we've discussed mass, we've discussed force, but we haven't had a very deep discussion of what weight means. It's a word that we use in everyday speech, and in physics it has a very particular meaning. We talk about the astronauts in now just the space station. We don't have a space shuttle to talk about, but in the space station, they're weightless. Has anyone heard of the Vomit Comet? If you haven't, you should Google it. It's kind of cool. The Vomit Comet is a plane, and NASA has one, and so does ESA, and I imagine that other countries like Japan probably have planes that do similar things. These are planes that get to very high altitudes, and then they cut their engines off so that the plane is in free fall. And you get, I think, on the order of 10 to 20 seconds of weightlessness. So what I want to discuss with you now is what one means by weightlessness. So to do that, I need to define what weight is. One quick anecdote. Have you ever seen, raise your hand if you've seen Apollo 13. It's a good movie. I like that movie. It turns out that all the scenes that occur where the astronauts are weightless were shot in the Vomit Comet. So that was not CGI. They weren't pretending to be weightless. They were actually in free fall in this plane. And from what I heard, Kevin Bacon did not really do so well in that circumstance. So I've actually seen an outtake of the consequences of that. So let's see what it means, why Kevin Bacon wasn't feeling so well while he shot Apollo 13. I'm going to start with something that we all know about the regular bathroom scale. So here's my representation of a bathroom scale. And here I am standing on the bathroom scale. So I'm not moving. I am stationary. I like to be on the joke too. No. So I'm stationary. I'm not moving. But so that means, from Newton's law, that the net force acting on me is 0. If you're distracting me, then I don't want to know what you're doing to other students. So don't, if you need to talk, you can talk outside. We got a force acting down on us. It's our weight, mg. The scale is supplying a force back up on us that we're going to call Fs. This is the equal and opposite force that we're acting down on the weight. Since we know that the net force on us is 0, we can write down that Fs minus mg equals 0. Simple equation. So we know that the scale is applying a force on us which is equal to our mass